Welcome, everybody, and welcome to Chapter 7. In this chapter, we will be looking at the introduction to sampling distributions. The objectives of these chapters are, at the end of this chapter, you will understand the concept of sampling error. You will also know how to determine the mean and standard deviation for the sampling distribution of the sampling mean. We will go through what that means. You will also understand the importance of the central limit theorem, which is a very important theorem in statistics. And at the end, we will determine the mean and standard deviation for the sampling distribution of a sampling proportion, which we would denote as p hat. So in a nutshell, what we will be looking at in this chapter are, we were looking at the sampling distribution of the mean and the sampling distribution of a proportion. Okay, so what is a sampling error? A sampling error is basically the difference between a measure computed from a sample, which is a statistic, and the corresponding measure computed from a population, which is a parameter. So the big picture here is that we have this very big population. Let's call this our population. And now from this population, we will draw out a small sample. So let's call this our sample. Now, so here we draw the sample, and let's say we drew the sample randomly. So random sample. Now, our population parameters, we have the population size, which is big N, and our sample size, which is small n. The goal of this chapter is to estimate our population from our sample. So what we have here is a sample, and we would use the sample to estimate what our population parameters would be. So our sample statistic that we'll have is, we have X bar, which is our sample statistic. And the question it would be, is our sample a true representation of our population? Now, our population parameters, we have mu, which is the population mean. We also, from a different, if we're looking at proportions, our sample proportion is denoted p hat, and our population proportion is denoted p. So these are the parameters of our population, and these are the statistics of our sample. So remember, P to P, population parameter, S to S, sample statistic. I think that's a good way to remember these things. Now, the difference between our sample mean and our population parameter is what is known as the sampling error. Right, so that's the sampling error. So X bar is the sample mean and mu is the population mean. Okay. Now we know what a sampling error is the difference between a measure computed from a sample, which is a statistic such as the sample mean or the sample proportion, and the corresponding measure computed from the population, a parameter such as the population mean or population proportion. Now, we will only focus on two statistics in this chapter. So the sampling error for means and also the sampling error for proportions. So we are focusing on means and proportions. Now, the sampling error for means is basically this difference, and for proportion, it's similar. So it's going to be the population, the sample proportion minus the population proportion. All right, cool. Next, let's look at an example. So let's say we have a student test course. So we have 62 students took a business statistics midterm exam. Now, the score below reflects the population of interest. Now, we have big N here, which is the population size. 62 students, not so much. So we can explore this population. Now, if I have 10,000 students, that gets a that, and let's say I have a different study in mind, it might be very hard to gather data from or investigate that large sample, that large population. And what we will focus then on will be drawing samples from the population in order to estimate the population. However, let's look at this example. So here we have 62 students who took a business statistics midterm exam. And next, let's order these in from the minimum. We can see score is 29. And wow, we have 3 students that scored 100. Now, recall from chapter 3, we looked at how to find the median, the first quartile, and the third quartile. So you can do that yourself. However, we will first find the population mean and also the population standard deviation from this data. And if you recall from chapter 3, we looked at how to find the population mean and also how to find the population standard deviation. Finding the population standard deviation is a little bit different from finding the sample standard deviation. So we looked at this. Now, to compute the population mean, it's simply the sum of all the scores divided by the sample, by the population size. So the sum of all the scores divided by the population size, and that would give us 71.43. So that is the population mean, mu. Now, what about the standard deviation? If you remember, we came up with this formula, and as I said, you don't have to remember this formula because we will, in this class, use softwares like Minitab to compute this for us, okay? However, there is a difference between a population standard deviation and a sample standard deviation. If we were to find the sample standard deviation, which is S, recall this is going to be equals to the square root of the sum of I is equals to 1 all the way to the sample size of n, xi minus x bar. So that's the sample mean squared. But this time around is going to be divided by n minus 1. We looked at this in chapter 3, just trying to show you the difference. So that when you use Minitab and say you determine the standard deviation, you take into consideration, is it computing the population standard deviation or is it computing the sample standard deviation? There is a difference. Now for the mean, of course, it's going to be consistent because you're just finding the sum of all the scores divided by the population size in this case or the sample size. So if it was a sample, it's going to be small n. All right. So we have that the population standard deviation for these student test score is 16.80. All right. So our population parameters, we have the mean is 71.43 and the standard deviation is 16.80. So the unit here is the score, test scores. Now let's look at the histogram of these of our test scores. So the midterm exam scores population distribution looks like this, where the mean is somewhere in the center, and this is the standard deviation. And of course, this distribution isn't completely very normal, you know. So this is what it looks like. However, to illustrate, so let's illustrate the concept of sampling error. Now recall that we have these 62 students in the class. However, let's say we want to investigate the scores of students by just randomly sampling 5 students from of all the students. So which means that I randomly select 5 students, I compute their mean, and the question is, will the mean of these 5 students estimate the population mean? That's what we want to investigate. Now, so here, this is our let's say this was drawn as a simple random sample without replacements, and we computed the mean of this sample. We have 72.80. You can see that it's not so close. It's pretty close to the population mean, and the difference is pretty small. So what our goal is to minimize the sampling error. So the smaller the sampling error, the closer our estimates to the population. So like I said, the idea of this chapter is to use a sample to estimate a population. So we want to use a sample to estimate a population. All right. Now, what if we decide, let's look at what we just did there. So sampling error occurs because the sample is not a perfect representation of the population. Now, we have the population mean is 71.43. The sample mean is 72.80. This is the difference. How do we interpret this difference? We can see here that the sample mean is only 1.37 points higher than the population mean. This sample mean is not a bad representation of the population mean. Now, what if we drew a different random sample from this population, and we're still using a sample size of n is equals to 5? Now, in our second draw, which is here, we have the sample, the sample mean is now 54.80, but look at this. This is much bigger. The sampling error is much bigger. So in this case here, we can see that the sample mean is only 54.80 and is 16.63 points lower than the population mean. This sample would be misleading value for the center of the population. Okay, so we can't just say we randomly draw out 5 samples, we find the mean and say that's the mean of the population. There's more that we have to do in order to come to the right conclusion. Again, here is the population mean. The sample mean is 54.80, and the sampling error, which is the difference between the sample mean and the population mean, is this. Now let's go ahead and repeat this step for 3 more samples. And so let's say we have 5 samples here. And as you can see, here's a sampling error. So it kind of fluctuates. Some are close to the population mean and some are a little bit off. So the population mean again is 71.43. And as you can see, depending on which sample is selected, the sampling error is quite small or very large. Okay? Let's take 200 random sample and calculate the sample mean. So think about this as a simulation. So we are running a simulation. Now we're taking 200 random sample and we calculate the sample mean of 200 random sample. And again, our sample size of n is equals to 5. So looking at just the first 5, you can see that fluctuation as we noted earlier. And if you eyeball the other values, you can see that there is that fluctuation. It's not always very close to the population mean. Now, one of the beauty of the sampling distribution of the means here, which we're going to look at, is that if we find the mean of all of the samples, it will actually be much closer to the population mean. So here we calculate the sampling error for the 200 different samples. Of course, again, this is just a repetition to show you that there is that fluctuation. And again, if we develop a histogram of the sample means, if you develop a histogram of these sample means, the histogram will be close to being normally distributed. That's something very interesting that we're to explore. So we have this distribution looks kind of, you can fit in a bell-shaped curve around this, right? And we can find the mean of the sampling distribution. So this is our sampling distribution, and from our sampling distribution we can find the mean, and we can also find, so we can find the mean. Let me clean that. So we can find the mean of our sampling distribution, and we can also find what we call the standard error of our sampling distribution. So this was going to be called the standard error. So the mean of the sampling distribution, again, recall, is this, and the standard error of the sampling distribution, so this is the standard error. It tells us how many standard error value is from the mean. So the standard error is this. So you can think of it as a standard deviation, but the standard deviation of our sampling distribution, we generally call it the standard error, okay? So when you see the term standard error. Now, if you're using Minitab, you want to ensure that you differentiate between when you're entering a standard error or when you're entering a standard deviation. The box where you're going to enter it would always be labeled standard deviation, but you should know when it's the standard error or the standard deviation. Now, generally, when we are looking at a sampling distribution, so the standard deviation is called the standard error. All right. So recall, so looking at this is what we have. Okay. All right. So we're going to show you a way of finding the standard error as we move along. So in conclusion, what we have seen so far is that the sampling error can be small or large, and positive or negative. So, which is the amount of error varies. In addition, we've seen that the sampling error depends on which sample is selected. The average of the sample means is approximately equal to the population mean. Look at it here. So this is the average of all the sample mean. And as you can see here, 71.25 is much closer to the population mean. Fantastic, right? I think that's amazing. Okay. And what we'll see later on is that we only have, each of our samples had a size of n is equals to 5. What happens if we increase n from, say, 5 to 10? All right, we will see that next. So the average of the sample means is approximately equals to the population mean. So that shows that we can use the sampling, we can estimate our population mean from the distributions of our sample means. Now, the variation in the sample means is less than the variation in the population. Again, as you can see, this is the population standard deviation, but this is the standard error of the sampling distribution, and this is much smaller than this. So we can say that this estimates that, but we can say that the sample mean estimates the population mean. So that's something we should take into consideration. So the sample, and the same thing also would apply for proportion, which we will see that the sample proportion will be a good estimate for the population proportion, and the sample mean, as we can see here, is a good estimator for the population mean. However, the sample variance is the sample variance or the sample standard deviation is not a good estimator for the population standard deviation. Okay, and so let's move on. And what else did we discover here? The last one here we've seen is that the distribution of sample means is approximately normal, irrespective of the population distribution. Now let's repeat this exercise with the student test. And now this time around, we are going to draw a sample of size n is equals to 10. And let's see the difference here. So first, 5 samples of size n is equals to 10. So we have this. And again, you can see that the sampling error still fluctuates as we've seen previously. And yeah, the mean. So now let's run a simulation of 200 random samples and calculate the sample mean. So we have 200 random samples, and now let's calculate the sample mean. Here is the sampling error. You can see there's that fluctuation. However, when we look at the distribution, it looks normally distributed. You can fit a normal a bell-shaped curve around. But this time around, the sampling distribution mean is much closer to the population parameter, the population mean, when as n increases. So if you recall, when n was equals to 5, this was a little bit smaller. And now that n is equals to 10, this is much closer to the population mean. So which means that as n increases, as we will see, as n increases, the standard error decreases. So as n increases, the standard error decreases. All right. So what we've seen here is that the sampling error can be small or large, and positive or negative. The amount of error varies. The sampling error depends on which sample is selected. The average of the sample means is approximately equal to the population mean. The variation in the sample means is less than the variation in the population mean. Again, that's what we can see from here. So as we increase n, this is even smaller than when n is equals to 5. And the sampling distribution is approximately normal. And finally, larger sample sizes result in less variability in the distribution of sample means. That's a very important concept. And we will look at some theorems that really brings this into focus. All right, so a recap on what we've done. So given that the population distribution looks like this, and we drew a sample of n is equals to 5, here histogram, the sampling distributions of the mean, the histogram, was normally distributed. And the sampling distribution mean is a good estimate of the population mean. As the sample size also increases to 10, what you see here is that this is even much closer to the population mean than when n is equals to 5. Now, as n increases, the standard error decreases. So this is less than this. So that's what one of the things we can see here. And this would lead us to the whole concept of the law of large numbers, you know. So as n increases, the variability decreases. The standard error decreases as n increases. All right. Now let's look at a different example of a mutual fund portfolio example, which is in your textbook. Looking at the distribution of the data, we have a mean of 2.505 and a standard deviation of this. So let's assume that we decide to draw a sample of a random, we look at 500 sample in which each sample size is of size n. Now, what we can see is that this distribution is approximately normal, and that the sampling distribution mean, the mean of the sampling distribution, is a good estimate of the population mean. And of course, as this n increases, so let's say if n gets to like 30, this will be much closer to this than what we have right here. Now, when the population distribution is skewed, so this kind of right skewed, we might want to increase n to a value more than 30. And this is based on some theoretical findings. And that way, we would have a much closer normal approximation. And when we have a normal approximation, it means that we can use the normality assumption to find probabilities. You know, in the previous chapter, we looked at how to find the probabilities, and really that's where we are headed to. So we can find the probabilities of different of the area under this normal curve. So using the knowledge we learned from the previous chapter. Okay, so let's look at the different theorems. So the first theorem here is that for any population, the average value of all possible sample means computed from possible random samples of a given size from the population equals the population mean. Now, again, this is expressed as this. So as the sample size, as remember, as n, as the sample size increases, gets very large, this becomes really true. Okay. So here we can see that the average of the sample means is equals to the population mean. This is actually known as the law of large numbers. So this is the law of large numbers. Okay. As you've noticed, we're using the PowerPoint this time around. Just wanted to make it a little change and simply let's see how it goes. I hope everything is going on well and you're well relaxed. If there are any questions, remember you can always contact me by email and through the other means that we have in the class. All right. So the previous examples were simulations based on only a few of the possible samples of a given size that could have been taken from the population. even then, the results closely match what Theorem 1 says. So this is Theorem 1. So when we had n is equals to 5 and n is equals to 10, what we saw here was that the average of the sample mean was approximately equal to the population mean. Okay. Now, Theorem 2 states that for any population, the standard deviation of the possible sample means. Now, the standard deviation of the possible sample means is what we call the standard error. Computed for all possible random samples of size n is equal to the population standard deviation divided by the square root of the sample size. So this is known as the square root law, in case you hear about it, the square root law. Now, the square root law states, as you can see here, that as n increases, what happens to the standard error? The standard error decreases. So this is the square root law. Okay? As n increases, the standard error decreases. Recall that we used the other formula from chapter 3 to compute the standard error. You could simply just compute it using the sigma divided by the square root of n. So sigma here is the population standard deviation divided by the square root of n. And n is the sample size. So the previous examples were simulated based on only a few of the possible samples of a given size that could have been taken from the population. Even then, the results closely match what Theorem 2 says, okay? And you can use your calculator to test it out, but I'll show you in the next slide. So we have n is equals to 5. Now, if you what we computed before, we had 7.91. Now, using this with your calculator, you have 7.51, which is close to 7.91 using the formula. And also, this will give you 5.31, which is close to 5.12, which we got with the formula. Now, moving forward, this is what you're going to do. You're going to use this Theorem 2 to compute the standard error. You don't have to use that complicated formula. Just find sigma divided by the square root of n, and that's what we will use moving forward in determining the standard error. All right, cool. So next, Theorem 3. If a population is normally distributed with mean mu and standard error deviation sigma, the sampling distribution of the sample mean, so the sample distribution of the sample mean x bar is also normally distributed with a mean equals to the population mean. And that's what we got from Theorem 1. And the standard deviation, so the population standard deviation divided by, so the standard deviation equal and I always like to call this the standard error. So equals the population standard deviation divided by the square root of the sample size. So refer to this as the standard error. So this is the standard error. All right. So what we established here, and this is pretty small, this is from the textbook. So given the population distribution, when n is 5, you can see that the standard error shrinks a little bit, and as n tends to 1 is equals to 100, the spread is much smaller. When n is equals to 20, it's even much narrower. Okay, so that's what we can see from this simulation. All right. Now we are headed to a new section, the whole concept of the central limit theorem, which is really the brain behind statistics. So this theorem states that, and this is based on all we've done, for simple random samples of n observations taken from a population with mean mu and standard deviation sigma, regardless of the population's distribution, provided the sample size is sufficiently large, the distribution of the sample means is approximately normal with a mean equals to the population mean and a standard deviation equals to, or the standard error equals to the population standard deviation divided by the square root of the sample size. The larger the sample size, the better the approximation to the normal distribution. And when that is the case, we can see that the central limit theorem refers to large samples drawn with replacements, and the results will be approximate, will follow a normal curve. So the results will be approximately follow a normal curve. And since that's the case, we can use normal approximations to compute probabilities. And that's what we're going to do next. So the key concept here is that regardless of population distribution shape, if sample size is sufficiently large, sampling distribution will be approximately normal. So that's the key concepts. And as I said, we can use normal approximations to compute probabilities. All right, so let's look at some example. So here we have, this is the population distribution that looks very uniform. It's uniform. And when n is, the sample size of n is equals to 2, we have a distribution that looks like a triangle, kind of symmetrical. But as n increases to 5, we have a distribution that looks like a bell-shaped curve. So this is the sampling distribution. So yeah, let's take the population was ages, and we had 3 people, 3 children. One is 1 year old, 2 years old, and 5 years old. And now we drew a sample distribution. So let's say one of our samples is 1 and 2. And yeah, let's take a different sample, and let's say with replacements. So we have 1, 1, 2, 5, 5, or something like that. Okay. Now we can generate multiple samples. That will be 2 to the power of 5, and then compute the distributions. Let me take this away for now. But what I'm just trying to show here is typically what we're meaning by a sample. So this sample size is n is equals to 2. This sample size n is equals to 5. And the higher the sample, the more the distribution tends towards a normal distribution. So it's approximately normal. Again, if the population distribution looks triangular, as n is equals to 5, we can see this is approximately normal, and as n tends to 30, now this is even more, the spread becomes much smaller, and it's approximately normal. And once more, if we have a skewed distribution, the sampling distribution would always be close to being normal. Now, if the sample size is small, it's not going to be really normal, but as n increases, and as we would say to about 30, the distribution will become more normal. So when your population distribution, which we don't always know, is skewed, then we really want to have a sample size, a very high sample size, and we normally recommend 30 or more. Okay. because we don't really know what the population distribution might look like, in order to have a good estimation, it's recommended to draw a sample of about size 30. All right, so the sample size must be sufficiently large. If the population is quite symmetric, then sample sizes as small as 2 or 3 can provide a normally distributed sampling distribution. If the population is highly skewed or otherwise irregularly shaped, this requires a much larger sample size. So a conservative definition of a sufficiently large sample size is n is greater or equals to 30. Okay? Let's get into the more fun parts. So now that we know that we can have this normal approximation, how do we compute probabilities? Now we're getting back to our z-score. Remember the z-score? We're back to it again. And you all recall how to find the z-score. Remember that the z-score is, you can recall z is equals to x minus mu divided by sigma. And this is for an individual data value of x. But here we are looking at a sampling distribution, which is x bar. So this will be a little bit different. So the relative distance that a given sample mean is from the center can be determined by standardizing the sampling distribution. Remember that the z-score has no unit, it's unitless, because if the units above was, let's say, points, and the units of standard deviation, which is the same unit as the mean, is also in points, that would cancel itself. So the z-score is unitless. We sometimes say z-value, z-score means the same thing. So the z-score measures the number of standard deviations a value is from the mean. That's what we said before. And in this case, since we are dealing with the mean, so this will be with the sampling distribution, our z is now equals to x bar minus mu of x bar divided by the standard error. Okay? And of course, from theorem 1, we know that mu of x bar is equals to the population mean, mu, and that sigma, let me put it here, sigma of x bar is equals to sigma divided by the square root of n. So this was from theorem 2, from theorem 1. So we recall this, and that's how we derived this. So that's our z. So remember that it's the standard deviation of the population divided by the square root of n. And that is the value that you're going to put into Minitab for those who are using Minitab. So this will now represent the standard deviation, known as the standard error, which you would use in Minitab. And that way, the knowledge you learned from the previous chapter becomes the same, because now that you know z, you can find those probabilities knowing z. Cool. So again, you know what this terms means. X bar is the sample mean, mu is the population mean, sigma is the population standard deviation, and small n is the sample size. Sweet. All right, it's time for me to fry some fish. So let's look at a different example of French fries. Right now, I'm just like you, I'm getting hungry. So a food processing company produces French fries for fast food outlets. The distribution of French fry length is thought to be normal with a mean of 4.0. So if you said it's thought to be normal, so let's draw something normal, and a mean of 4.0, and a standard deviation of 1. So what we are saying is that we have the distribution that is normally distributed, a mean of 4.0 inches, and a standard deviation of 1. Now, what is the probability of selecting a simple random sample of 100 fries with a sample mean exceeding 4.10. So when you're given this question, the first thing you want to do is write out the terms given and also understand what you're trying to find. So looking here, what is 100? 100 is the sample size. What is the population mean? The population mean is 4. What is the standard deviation of the population? That is 1. All right, that's what we have there. Now, what are we trying to find here? We are trying to find the probability that X bar, not X. So this is X bar is greater or equals to 4.1. That's what we're trying to find. It says, what is the probability of selecting a simple random sample of 100 fries? So N is equals to 100 with a sample mean exceeding 4.1. So this is what we're going to find. And so for these, we need to standardize this, find the z-score for 4.1 so that we can use our table, or you can use the calculator in order to find that probability. So here's the distribution. So we are trying, so if the mean here is 4, now 4.1 is somewhere around here. So the area of interest is this location. That's what we're interested in. That is the probability that X bar is greater than or equals to 4.1. And you can use Minitab. You should all be experts at this using Minitab to find the probabilities, or you can use a table. If you're using your table, remember it gives you the positive values. You're going to find this one first. When you know this area, in order to compute this area, you simply subtract this area from 0.5 because this is symmetrical. So this whole area to the right is 0.5. This area to the left is also 0.5. So if given that we know what point this is, and we find the z value for 4.1, then we can then go to the z table to determine this area. And with that, we subtract from 0.5 in order to get this area. If this is very confusing, remember, you can always meet with me during our student hours, and I would show you more examples, and I will create a different video where I would show you how to do this in Minitab as well. All right. So looking at this now, let's find our z. So our z is 1.0. So basically the value is one standard deviation away from the mean. Now let's draw this. So let's look at what we're interested in. So the area that we're interested in is the area shaded black. So this is the probability that z is greater than 1. Now you can use your table to find that. So if you use your table, you'll find out that this area is 0.3413. And when you subtract from 0.5, that gives us this area. Cool, right? Sweet. Okay. So since that is clear, let's move further. What is the probability that the mean of the sample of n is equals to 64 fries is less than 3.85? So here now we are changing the question a little bit, and here so a sample of, just a moment, let me go back to see. All right. So yeah, this should be 64. So a sample of, but it looks like the let's change this. Let's keep it at 100 and simply just change this. We are still using 100, n is 100 and not 64. But now what we are changing here is we want to find the probability that of fries is less than 3.85. So this is what we're trying to find here. So if the mean here is 4, then somewhere around here is 3.85. So the area that we're interested in is this area. Okay, now the Z table in your textbook only gives you positive values. So what that means is that when you find the Z value of this, which we're going to find next, you can then find, that this area will be equals to this area once we find the point that is symmetrical equivalent to this point towards the right, since this distribution is symmetrical. And then again, we can find this area from the table, and that way find this area. Right now, we're in the X bar distribution. Let's standardize the sampling distribution. So given that we have this, n is 100, not 64, and mu is 4.0, and sigma is 1. So solving for this, we have that Z is now 1.50. And looking at this, if this is negative 1.5, this point here is negative 1.5. Now we can have this is positive 1.5. Let me use my calculator to verify what was done with this text. So we have 3.85 minus 4 divided by the square root of 100. And we have 3.5 minus 4, sorry, divided by sigma divided by this. So no, let me go back. Divided by 1, which is the standard deviation, divided by square root of 100. So that gives us, try it one more time, 3.85 minus 4 divided by 1 divided by the square root of 100. So if you do that with your calculator, you will have negative 1.50. Okay, so that is confirmed. Just want to confirm with you so that you won't send me an email that, no, there's something wrong with your computation. It's correct. It was well checked. So it's negative 1.50, and that is why we have it here. And this is the area of interest. However, as I said, you can also look towards the right. So which means that this is the area that we want that's of interest. Now, again, if you're using the table in your textbook, it gives you this area. Once you know this area, you subtract it from 0.5, and that will give you this area. Okay? Or you can use Minitab and simply just select the area to the right of 1.50, and that would also give you the same answer. And you can see that in the next video where I show you how to use Minitab to solve these problems. All right, so like I said, the area we have for the probability of 0 to 1.5, or the same thing as 0 to negative 1.5, is 0.432. Now you subtract it from 0.5, that gives us this area, same thing as this. So this should be pretty clear right now. And in the video of Minitab, I'll show you how to make it even much simpler than using the table. So for those who want to use the table, watch the previous chapter, chapter 6, where I showed you how to use a table. And I think I also showed you how to use the calculator. Now, In the next video, I will create a different video on how to use Minitab to solve for these problems as well. Okay. Now let's go into the final section for this class, sampling distributions of a proportion. So the population proportion is the fraction of values in a population that have a specific attribute. And the sample proportion is the fraction of items in a sample that have the attribute of interest. Now, the population proportion is denoted P, and we have that it's X divided by N, where X is the number of items in the population having the attribute of interest. So the number of items in the population having the attribute of interest is X. And N is the population size. Big N is the population size. Now for the proportion, for the sample proportion, P hat is a sample proportion, and X is also the number of items in the sample, this time around, not population, but sample with the attributes of interest. And small n is the sample size. Okay, cool. So let's look at what we spoke about earlier. How do you determine the sampling error for a proportion? Remember, we stated it this way, where P hat is the sample proportion and P is the population proportion. So what do? Determine the population proportion, compute the sample proportion, and then compute the sampling error. This is what you're going to see and do in your homework assignments. All right. So the best estimate of the population proportion will be P hat, the sample proportion. This is going to be similar to what we saw with the mean. Any inference about how close your estimate is to the true population value will be based on the distribution of the sample proportion, as we saw in the distribution of the sample mean. So now the underlying distribution here is binomial. Remember that when you are dealing with proportion, it's either we have success or failure. Now, one thing to check as you go on, if the sample size is sufficiently large, and by sufficiently large, we are saying that n times p is greater than or equals to 5, and n times q, remember that q is equals to 1 minus p, so n times q is greater than or equals to 5. If that is the case, the distribution, we would have a normal distribution. So the normal distribution can be used as a reasonable approximation to the discrete binomial distribution. So in that case, we are also going to use the normal as approximation in order to compute probabilities. Okay? All right, so let's see how it goes with some example. So the first thing you have to do, remember, is to check this. These are the requirements. So ensure that n times p is greater than or equals to 5, and also ensure that n times q is greater than or equals to 5. Before you proceed in computing any probability, because when this is the case, it means that the distribution, the binomial distribution will become approximately normal. All right. So how do we find the sampling distribution of p hat? It says p bar, I call it p hat. Wearing a hat. Okay. So the sampling distribution of the proportion p hat is equals to the population proportion. So that's the expected value of the proportion. And the standard error is equals to this. And you can, so this is simply saying that This is the square root of P times Q over N. Another way to see these in terms of what we've done so far is to represent this in the context of the variance. Now, the variance would be sigma P hat squared is equals to let's leave it as this. I just want to show some similarity to the mean. So let's look at the similarity in the context of the standard deviation. So this is simply equals to the square root of PQ divided by the square root of N, right? Now, what is the square root of PQ? That is what's the square root of PQ? That is the standard deviation of the proportion. So recall that we said the standard error is sigma. So this is going to be sigma of P hat divided by, so this looks like sigma divided by the square root of N. But no, let's remove that. Let me put it again. So this would be not the sigma of P hat, but just the standard deviation divided by the square root of N. So the sigma of P hat is equals to the population standard deviation of the divided by the square root of N. That's what we saw for the mean. So it's similar because we recall from the last two chapters we said that sigma in terms of proportion is equals to square root of square root of P times Q. All right, just wanted to see the similarity, and putting it this way, maybe you will not forget. All right, so P is a population proportion, N is a sample size, and P hat is the sample proportion. So let's look at an example to bring this to context. So according to past records for a large national retail chain, the proportion of customers who pay for their merchandise with a debit card is 0.6. Suppose a particular store within the chain examines a sample of N is equals to 100. Or is equals to 100 purchases and observes for the 8 customers used a debit card. What is the probability of a sample proportion of 0.48 or less if the true population proportion is 0.6? All right, so we've seen this question. How do we interpret it? What are we trying to find? So if you look here, what is the probability of a sample proportion 0.48 0.48 or less if the true population proportion is 0.6? So what we're trying to find here is simply the probability that P hat is less than or equals to 0.48. That's what we're trying to find. Okay, so now that we know what we're trying to find, now let's go ahead now to find here I showed you how to find the standard error, so which is the sample distribution standard error or standard deviation. All right, so we recall that the mean of the population, the sampling distribution mean for the sample proportion is equals to the population proportion, and which we established from Theorem 1, which is equals to 0.6 as given in the question. Now the next step here is to find the standard error. And recall it's the square root of P times Q over N. And so that gives us this. Okay, so we know this. So since we know this, we know that to find Z is going to be P hat minus P divided by sigma of P hat. So that's why we have to find the standard error first. So next, what are we trying to find? We're trying to find the probability that P hat is less than or equals to 0.48. So we are interested in this area. So next, we're going to find the Z value for this P hat. So that will be 0.48 minus 0.6 divided by 0.155. Now, when we do that, so this is standardizing the sampling distribution, we have negative 0.77, okay? All right, and now we know that we this is the point we are interested in, and we're interested in this area shaded in black. All right. So again, we can look at this point at the right where we have positive 0.77 around here. Draw a line around here, and the area that we're also interested would be this. So it will give us the same value. And once more, you can use your table to find this area and subtract it from 0.5 in order to get this area of interest. Now, this area is equal to the same area because this normal distribution is symmetrical. So when we do that, this area is 0.2794. And when we subtract from 0.5, we get this area, which is also equal to this area of 0.2206. Okay. So with that, so that's the probability. Now let's look at one last example. Income task. And this is an example in which the distribution of the population is a bit skewed. So let's say a big problem for taxpayers has been the recent increase in fraudulent tax returns being filed with the IRS in the name of taxpayers. Suppose the IRS believes that 15% of all taxpayers will be affected in 2016, assuming the true proportion of taxpayers who gets tagged is 0.15. What does that mean? We're saying that P is equals to 0.15. What is the probability that more than 40 in a random sample of 200 will have had this experience? All right, so let's break this down and understand what we're trying to find. So what is X? So the probability that more than 40 in a random sample of 200 will have had the experience. So what we're X is what? What did we say X is? So X is the number of items in the population having the attribute of interest. So X here is 40. And what is N? N is 200. So what does that mean? That our P hat is simply X over N. Okay? All right, so that's what I have shown here. So P is this and P hat is that. So so now that we've established this, what are we trying to find? What is the probability that more than 40 in a random sample of 200 will have had this experience? So what we're trying to find is the probability that P hat is greater than 0.2. Okay, that's what we're trying to find. Exactly. So that's what I have here. So what's the probability that p hat is greater than 0.2? Again, the first things to do is what? Compute n times p and also compute n times q. If n times p should be greater than or equals 5, n times q should be greater than or equals to 5. If that's the case, then we can go ahead to find the z values. Okay, so we have, this is p. We can find our standard error using this expression, which we've established. And now we know that what we are looking for is this area, the probability that p hat is greater than 0.2. So now we're going to find the z value for 0.2. So this distribution is a p hat distribution. So we now want to find this, convert this to the z distribution. So we standardize the sampling distribution. So once we standardize the sampling distribution, we find the z-score to standardize it. And the z-score now here is 1.98. So which means that we are looking for this small area to the right. Now, again, you can use your standard normal table. You can use Minitab. You can use your calculator in order to find this area. If you're using your textbook, you're going to first find this area. And again, you subtract from 0.5 to get this area of interest. So in your textbook, this area here is 0.4761, and the area of interest is 0.05 minus that, and that gives us 0.0239. Fantastic. So with this, when we have 1.98, you can think of these again in terms of the, is that rare? Is that likely, unlikely? And you can expand on that thinking, you know. So after you find the z-scores, you can also think about the concept of rare events. Remember the rare event rule, that which is likely is within 2 standard deviation from the mean. That which is unlikely is more than 2 standard deviation from the mean. So that's something else you can think about. But at this point, we are really building up into the whole idea of statistical inference, where we will look at hypothesis. You know, an hypothesis is a statement that you want to prove, which is either true and false. And in order to prove our hypothesis, we need to draw evidence in order to test our hypothesis. Now, if you start with an assumption and the probability of your assumption is small, then it's most likely that it's wrong. Now, if under a given assumption, the probability of an event is really small, then that assumption is probably wrong, okay? Now, in the next chapter, we will be looking at confidence intervals, and subsequently we'll look at hypothesis testing. So at this point, we've come to the end of this lecture, and I wish you all a most happy day, whatever time you're watching. Go out and have some fun, play any instrument. Enjoy life. Take it easy. Do some yoga. Relax. And go back again and watch this material. And the next time you watch it, you'll be amazed how the whole concept will take on form. So see you in my next video.